on, here we go. All right, so we're evaluating this limit. Never not first. You got the limit to infinity of the log minus the log. If you plug in an infinity to the first term, 3 times infinity is infinity, infinity plus 1 is infinity, the absolute value is infinity. What is the natural log of infinity? In other words, what does the graph of the natural log do as you go to the right? It keeps going up, 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 right, to infinity. So this goes to infinity the first term, and similarly, the second term goes to infinity. So this becomes infinity minus infinity, and that's indeterminate. If it had been infinity plus infinity, what's infinity plus another infinity? That's infinity. If it were negative infinity minus infinity, those are going in the same direction. That's negative infinity. But this has like the implication of canceling out, like 0 over 0 and infinity over infinity dividing out. You have to turn this indeterminate form into one of the 2 quotient varieties that we had. And rather than get a common denominator like we did yesterday, we have to accomplish this one by using the rules of logs. So we already studied logs this year, right? So remember that the natural log of x times y is the natural log of x plus the natural log of y. And similarly, the natural log of x divided by y is the natural log of x minus the natural log of y. And then the other one that was important was the natural log of x to the nth power is n times the natural log of x. All right, so when you go from left to right, that's expanding. When you go from right to left, that's condensing, right? Now, normally when we were taking the derivative of log functions, we like to go from left to right. Remember that function f of u? And I was like, no, I'm not doing that f of u function. There's a natural log there. We can expand it out and turn the mountain into just a bunch of individual molehills. But now we want to go the other direction, okay? So here's what we're going to do. We showed the infinity minus infinity. We're not doing L'Hopital's rule yet. We're just doing some rearranging of things on the first one. So since they both have log base e, I'll pull one of them out. And since the absolute value, I'll keep it. The positive terms argument goes in the numerator, and the negative terms argument goes in the denominator, right? That's how we condense it. Now that is progress, and that's an important insight right there. That is progress because we changed from 2 terms now to a single term. Let's try direct substitution again. If I plug in infinity now, the top's going to give me what? Infinity, and the bottom's going to give me infinity. Oh crap, what's infinity divided by infinity? Yeah, it's indeterminate, but how do I take the natural log of an indeterminate thing? Oh, well, remember we can do this. This is composition. So if you want to write it, you could bring that log inside. This is the natural log of the absolute value of the limit as x goes to infinity of 3x plus 1 all over x minus 5. That was that other property of logs that we were allowed to do, okay? Now I've kind of turned it into a small problem again. It is going to be infinity over infinity, so we could technically use L'Hopital's rule on there. Let's just do that in our head. What would be the derivative of the top? 3. What would be the derivative of the bottom? 1. What's 3 divided by 1? 3. So it works. You wouldn't have to show that, okay? Because there was the other way that we talked about it, right? When the degrees of the top and bottom are the same degree, it's leading coefficient over leading coefficient. So however you get to 3, if you want to use L'Hopital rule, you're going to have to write it out, but in this case, it's not required, okay? So we end up with the natural log of 3. Is that the answer? Yeah, that's the answer. Yeah. So those properties of logs, very, very helpful when we are evaluating limits. They turn differences into quotients, and quotients are the 2 varieties that we need for L'Hopital's rule. Okay, so that's a good review. We'll start doing like spiral review like this as we move forward. All right, so now getting back to where we were, I did update the whatever I didn't have updated, the modified worksheet or the modified notes. I don't remember the notes. The notes are, so there should be red writing on the notes now. If you re-download it, I apologize for not doing it. But we were talking about continuous functions, the sign of f prime. If it's positive, a function's increasing. If it's negative, the function's decreasing on that interval, and that can only happen at a critical value. But if it has discontinuities, it could also happen there. All right. So what we're doing in this section, here's the goal of the section. In fact, let me go ahead and read this to you. I will, we will. Let's get this on tape. Ew. I will, we will. We're going to find critical values and discontinuities of function. We're going to find intervals of increasing and decreasing of the function. We're going to find the absolute extrema of a function, and we're going to find the local extrema of a function. Okay, that's what we're doing today. If that helps you compartmentalize what we're doing, so be it. Supposedly that's the key that unlocks y'all's learning. Me saying that to y'all. Ew. All right. Now we're going to do 2 and 1 here. This is part of our streamlining. The first derivative test. This is like super, I would add duper to it. You know, I don't want to overstate it, but super duper important. Okay. The first derivative test is a test for relative or local extrema for continuous functions. That's what it is. So when you use the first derivative test, you are looking at evidence to determine if a function has a local maximum at an x value, a local minimum at an x value, or neither, right? And then you're going to have to justify. Now, not every critical value is going to be a local max or min, right? We talked about how you can have a horizontal tangent like this. That's not one, but it could be like this, or it could be like this. And of course, it could also be, you know, like, it could also be like this, or like this. In each of those cases, those dots occur at critical values, right? But if I don't see the graph, how can the first derivative, knowledge of the first derivative, how can it help me determine if they're local max or mins? Well, let's just look at it. In this case right here, that is not a local max nor a local min, right? Because immediately to the left, we have values that are smaller, and immediately to the right, we have values that are bigger. That's the litmus test we used earlier when we had the graph. But now we're going to be doing it by instrumentation only. If you've ever flown a plane without being able to see, wow, I don't know if anyone has anyone done that. You have to fly by instruments, right? You have to use your gauges. So here's what we know. Immediately to the left of that critical value, we'll call this x equals critical value. What do I know about the sign of the derivative? Well, f prime is greater than 0 to the left, yeah? The function is increasing to the left because f prime is positive. And immediately to the right, what do we know about the derivative? It's also positive. So that's how the first derivative will help us. If I know the sign of the first derivative immediately to the left and right of a critical value, I can determine if it goes from increasing to increasing and is not a critical value. I can tell if it goes from increasing to decreasing. I can tell if it goes from decreasing to increasing. In those last 2 cases, those would be relative max and mins. And we could do the same analysis on these critical values where it's not differentiable. Positive derivative, it increases on both sides. Positive derivative, negative derivative, positive derivative, okay? So when we do the first derivative test, we're going to have to write a sentence and justify. We're not going to say the words increasing, decreasing. We're going to say the sign of the derivative, okay? In other words, when you use the first derivative test, you have to talk about information from the first derivative, okay? Let me show you what I mean. Let's jump up here. Example 2, retreat. Find the open intervals on which this cubic polynomial is increasing and or decreasing, justify. And then I added this. Let's go ahead and find the x values of any local extrema, and we'll justify. Now you'll see that this is going to be a 2 and 1. We're going to get our information one time, and it's going to enable us to answer both of these questions. All right, first of all, let's size up the function. This is a polynomial function. Where is a polynomial function continuous? Everywhere. So are there any discontinuities? No, we want to look for those first because they're easy to overlook. No discontinuities. So if I can find the critical values of this continuous function, I will be able to test intervals between them because it can only change from increasing to decreasing or vice versa at a critical value. So how do I find critical values? I take the derivative and do what? Set it equal to 0, and always just at least consider where it might also be what? D and E, right? But a polynomial's derivative is another polynomial, so that's not going to be the case. But let's go ahead and do that. We'll find the derivative. When in doubt, take the derivative, right? This is calculus. X cubed becomes 3x squared. Multiply, you get 3x to the first. Now we'll just consider in our head. We'll just do it real quickly. Is that quadratic ever undefined? No. So now I can just set it equal to 0. If we were actually going to do it twice, we would kind of go off on a little stem here and rewrite it. But it's just equal to 0. And now when something's equal to 0 and you have more than one variable, you solve it by factoring, hopefully, right? Or at least the quadratic formula. So we'll pull out a 3x, and we could drop the equal on the left now, and we get x minus 1. And this is a good time to mentally redistribute to make sure you didn't make any mistakes, right? Do we get that? Do we get that? Yeah, life is good, right? And now from here, you could just pluck the values right out of there, right? So x equals 0, and I will go ahead and write x equals 1. Or you can just put 0, 1. Those are your critical values. Hey, boys, how are you? Looking good. Now, if we were doing the EVT, right? Remember the EVT was the extreme value? That was the game show. I want you to always associate the EVT with the game show. That's where you're trying to find the absolute extreme of a continuous function. If either of these contestants lived in the closed interval, we would want to know what their y value is there. And we would compare them to the y values of the endpoints. That's the EVT. We want to know if these guys are local maxes or local mins, okay? So here's what we're going to do. And this is going to be super important. We're going to make what's called a number line chart. A number line chart. Super important. I need to know what the sign of the first derivative is in between those two numbers. So here's the number line right here. Make a double bar column on the far left, because what we're going to do is we're going to choose some values of x, and we're going to look at the sign of f prime. Now, this is a test value, and this is just the sign. I typically don't write this. I just put x and f prime. But we're looking for test values of x, and we're looking for the sign of f prime. This right here is your number line. This is a number line, okay? A real number line. Let's go ahead and put those values 0 and 1 on the number line. By the well ordering principle, we know they're there and we know the order, right? So this might be where 0 is, and this might be where 1 is, yeah? Now here's what we want to do. To turn a number line into a chart, we just make those marks a little bit bigger. And now we put 0 right here and 1 up there. What we've done now with those marks is we've created these two rows. And our critical values are sitting high and mighty up at the top, looking down. So here's why the theorem is so important. The function can only change from increasing to decreasing or vice versa at a critical value. That's it. So if I know what the sign of f prime is to the left of 0, I know if it's increasing or decreasing everywhere to the left of 0. Same thing between 0 and 1, same thing to the right of 1. So we get to pick our own values. Any number now to the left of 0 will work. Any number between 0 and 1 will work. And any number to the right of 1 will work. So make it easy on yourself, right? What number should we pick? Any number to the left of 0? -1. I'm going to put it right there in that 1, 1 position. What's the value between 0 and 1? 1/2. So I'll put 1/2, maybe 0.5 would be better. I don't know. And then to the right of 1, 2 pi. Pi would work. 2 is great. Yeah. These are sacrificial values. We're using them one time and then thanks for your service, right? Here's a broken toaster. Now to find the sign of f prime, not the value. We don't want the value. We just want the sign. I have two different versions of f prime. This one and this one. Which one, top or bottom, is easier to find just the sign of and not the value? The top one will work, but you have to do some calculating. The bottom one is preferred because it is factored. It's factored. It's factored. So it breaks the problem into smaller pieces, because a negative times a negative is a positive, a negative times a positive is a negative, positive times that kind of stuff. So this is what I called earlier the full-fledged factored version of f prime. That's what this is, or the remember that? Yeah, that's what you want. So in the process of solving for 0, you don't want to divide both sides by 3. You don't want to like actually go through the algebra because you want it to be fully intact. And if you divided by 3, it wouldn't be fully intact, which wouldn't be a problem. But what if that were a -3 and you divided both sides by -3 and now it's gone? You want to always plug back into a fully intact factored version if you can of f prime. Okay, now watch how easy it is. We're going to take our test values. We're going to plug them into. We're going to see what the sign is. That woke Brody up. 3 times -1 is negative. Who cares? Got it? See it? -1 minus 1 is negative, who cares? What's a negative times a negative? A positive. So I put a plus sign in here. You could write the letters POS, whatever helps you. The number line chart is not graded. You don't get no credit for it, but it's the best way to organize your information so that you get credit for everything else. All right, plug in a 1/2. Which version's easier? I don't care. Plug in a 1/2. 3 times 1/2 is positive. Who cares? 1/2 minus 1 is negative. Who cares? Now, what's a positive times a negative? That's a negative. It's just the sign. We don't care about the value right now. The value tells us how fast it's going up. We just want to know if it's going up or down. And now you plug in a 2. Positive times positive is positive. Okay, so it turns out that the sign of the derivative did alternate at each interval. But that combination could be anything. You could have multiple critical values, and it could be plus, plus, minus, minus, plus, minus. It could be consecutive intervals. So this is all we need to answer both questions. Okay, let's go ahead and answer the questions. And this is where you have a complete sentence. Complete sentence. You really got to model this. Okay. F, that's the name of the function, is increasing, which you can abbreviate INC, on, and now how do we know where it's increasing? We go back to the number line chart, wherever it's positive. Now, here's where you got to be careful. Sometimes it's easy in haste to go back to your test values and use those. So after you use those, if you want to draw a line through them, you can, because we got to go back to these guys, right? If you want to circle them. So F is increasing on the interval everywhere to the left of 0. How do we write that? Negative infinity to 0. And we're listing open intervals. So there's that. Is there another one? Union 1 to infinity, right? Now, what I mean about making careless mistakes, because I've done it myself. If these guys get lost up there and you're looking at these, you could say it's increasing from negative infinity to -1, and then from 2 to infinity, which wouldn't be wrong, but it's not the entire interval. So once you use those sacrificial test values, make sure the critical values stand out. And decreasing on the interval between 0 and 1. Between them. And that can help you answer a free response question, or it can give you the information you need to answer a multiple choice question. They might ask, what are the intervals where F is increasing only or decreasing only? And you got it, right? All right, now for the first derivative test, we got it. We still got it, okay? Because watch, if a function has a derivative that goes from positive to negative, that means the function goes from increasing to the left to decreasing on the right, which means that has to be the location of a local what? Max. And if a function goes from decreasing to the left to increasing on the right, notice what I'm doing. I'm kind of transferring down the number line here. That has to be the location of a local min. And because those were both critical values that had horizontal tangents and not vertical tangents like cusps, we know they have to look like that. We have a hill and a valley. We've got it. So all we have to do is work on how do we get full credit? Well, again, in a complete sentence, F has a, let's do the local max. Local max, and you could say local max or relative max. Local has fewer letters, right? Could you just say a maximum? No, because that would be global, and we don't know if that's true. But F has a local max at x equals 0. It typically asks for the x values, but remember, if you ever want the y value that goes along with the x, you plug it back into where? The original function, not f prime. The original, it's the y value machine. You have a y value machine, and then you have a slope machine, okay? So if they ever ask for the y value, but it has a local maximum x equals 0 here, and then here's what you need to write. Because, I used to write since, but because is a little better. Because, and now you have to talk about a local argument, because f prime changes from positive to negative at x equals 0. Trust me 100%, if you say it like that, you'll get full credit. When I was an AP reader, I learned kind of a lot about the difference between getting the right answer and getting credit for the right answer. And this is kind of the way they want it, right? So F has a local max at X equals 0. That's generally a check for identifying it. But this is your justification right here. Because F prime changes from positive to negative, and then say it again at X equals 0. If you want to use a pronoun judiciously there, you could say at this point, but you must refer back to it. It's easier just to write at X equals 0 again, right? It's fewer keystrokes with your hand. What do you call that? Keystrokes with the hand. Hand strokes? No.
Strokes.
Strokes. There you go. Yeah, yeah. Yeah. So I just put at X equals 0 again. It's real easy. What you do not do is say because F prime goes from increasing to decreasing at X equals 0. You're not lying when you say that, but you're not justifying using first derivative information. Now, if you want to do that on the back end, that's just extra writing. Bless you. Because F prime changes from positive to negative X equals 0, which means F goes from increasing to decreasing. Now you're volunteering information and it's not wrong, but no credit for that. Okay, bless you. Go ahead and write the sentence now for the local minimum and we'll see how you do. Okay, use this as a template. Did you do it without looking at mine? Yeah. Good, good, good. No, because 2 is our test value. At 2, it's like here's 2 right here. This is 2. It's increasing on both sides. Here's 2, here's 1. So that's why once you choose those numbers, you got to go back to these. And it's tempting. That's why I draw these taller instead up here at the top. These are sacrificial. Try them one time and we're done. Sacrificial. Sacrifice them to the math gods. Yeah. Yeah, you can use local and relative interchangeably. So yeah, let's go through it, see how you did. I kind of changed it up a little bit, but again, the chart gets no points. But if you want to draw these little lines to help you visualize what you're doing, that's fine. Just never justify anything by saying the words increasing and decreasing when you're talking about change. Okay, F has a relative min or a local min at X equals 1. Check. Because F prime changes from negative to positive. Where? In France? No. Also at X equals 1. You got to say it twice. Here's where it exists because that also happens to be the same spot where this happens. And this is a local argument. You can't just say there's a relative min at X equals 1 because F prime is negative to the left and positive to the right. Because when you say negative to the left, that's not local, that's where? That's global, that's everywhere to the left. And when you say to the right, that's everywhere to the right, and that's not necessarily true. But when you say it changes from at, that they acknowledge that as a local argument. Immediately to the left, it's increasing. Immediately to the right, it's decreasing, so there's a local max there. All right, so you got to get that terminology down. All right, I think it's lunchtime. People are in the hallway. We got a minute, but we'll pick up here after lunch. This is not really hard. It's just a matter of getting the words right. We got to phrase that argument. Tomorrow we'll take C lunch, but we didn't plan on that today. So have a great lunch or B lunch. 3, 2, 1. All right, we back. So we left off. Did we finish that problem? I think so. Okay. Now, the one thing we did not do is I did not justify why F was increasing or decreasing. It said to do that. So let's just come back and kind of sneak that in there. F is increasing on these intervals. It's not typically asked for, but you want to be prepared. We'll say because what? How do we know that the function F is increasing on those intervals? What do we look at? F prime is what? Greater than 0 on these intervals. Very good. Now, in this case, that is a good pronoun to use. I don't want to have to rewrite those intervals. So you can use those pronouns judiciously, right? If you have a clearly defined antecedent that comes before it, you can use the pronoun. Just like if you refer to yourself in a sentence already, feel free to use the reflexive pronoun myself. But if you haven't, it's not the right word to use, right? Okay. Details matter, don't they? Yeah. And then F is decreasing on the interval from 0 to 1 because what? F prime is less than 0 on this interval. There's another judicious pronoun. Now, you can actually write out the words F prime, right? F prime, and you could say is negative. You could write that out. But if you put less than 0, it's using the language of math. So typically when you have to justify something, it's just a bunch of words with math evidence in it. All right. So there has to be something mathy in it. All right. You got the idea, right? It's a pretty easy idea. I was going to omit, we can skip that. I was going to omit example 3, but I think I'm going to bring it back into the fold. And I'm sorry you can't erase your big red lines there. So maybe you can write through it. I hope. Yeah. You never did. Okay. So, and I changed this during lunch. Part B is going to be pretty much the same, but we'll cross the bridge when we get there. Okay. So we're starting brand new and new. Now just write over it. Use a darker shade. It'll be cool. It'll be cool. You're like, please include. All right. Example 3. There's a quintic polynomial. Find the open intervals where F is increasing or decreasing. Justify. A polynomial is continuous everywhere, so it can only increase or decrease change at a critical value. There we go. How do we find critical values? Take the derivative, set it equal to 0, and consider where it might be undefined. But a polynomial is differentiable, and so are its derivatives. So let's just go right to it. F prime of x equals multiply, subtract, multiply, subtract, multiply, subtract. So we get 2x to the 4th minus 7x to the 3rd minus 4x squared plus nothing. Okay, that's never undefined, so we could just set it equal to 0 right there. And notice we turned a conditional equation into it when you set it equal to 0. Now I'm going to factor out a what? Common factor of x squared. And then I get, let's see, I'm left with a quadratic, 2x squared minus 7x minus 4 equals 0. And now that quadratic maybe can factor further. It's the fun type, right? Well, the leading coefficient is not 1. So it's got to be a 2x and a 1x. This 2 is prime. And then with 4, it's either the old 4-2 combo or the old 2-2 combo. So you can do trial and error or just figure it out. Everybody in here has a way to factor these types, right? You've practiced or you've struggled through it, but you've gotten through it. Huh? Yeah, okay, yeah. Without splitting the middle term, I'm just going to do the guess and check. I'm looking for, I want my product to be -4, and I want this to be a -7 on the sum. The inside and outside has to be -7. So if you try it a 2-2 combo, you know, they have, one of them has to be opposite signs. You get a 2x on the inside and a 4x on the outside. 4x plus 2x is only 7x, and 4x minus 2x is only 2x. So it's not going to be the 2-2 combo. So what could it be? Well, it could be the 4-1 or the 1-4. It could be the 1-4 or the 4-1. I'll just write both cases there. This gives us a 1x if I use the 1-4 combo and an 8. 8 plus 1 is 9, but 8 minus 1 is 7. So I like that combo. Let's just see what this gives us. This gives us a 4 and a 2. 4 plus 2 is only 6. So it's got to be the old 1-4 combo. So that's how I do it. And y'all being liquid in your thinking, right? The best and brightest on campus. If that helps, that's good. It's just really just trial and error. If you want to go off to the side and split the middle term, you could do target sum, target product. It's a lot more involved, but it works. I could show you all that if you want in tutorials. But anyway, now we get the sign. It has to be a -4 and +1. Okay, and then again, if you quickly FOIL first, outer, inner, last, you'll see that you get the top thing. Okay, this is completely factored. It's fully intact. I'm going to come back to this dude later. You stay there, F prime. If you still want to keep F prime associated with it, that's fine. There's nothing wrong with that. But now we rattle off the critical values. X equals what? -1, 4, and the one that most people overlook, 0. Yeah. He gets kind of lost in the shuffle because he doesn't stand out with parentheses like the other. -1/2. Yeah, I thought someone said -1 and I just wrote it down. I didn't check. Thank you. -1/2. Yeah. But 0 is really x minus 0 quantity squared. So 0, -1/2, and 4. Those are your 3 critical values. All right. If we were doing EVT, maybe if those live on the open interval, we'd include them, find their y values. But we're going to do a number line chart now. Okay, here we go. So we have x and f prime, and we got to put them in order, right? That's why it's a number line graph. So -1/2 is the smallest, 0 is the next largest, and 4 is up here. So with 3 critical values, we create 4 intervals to test. That's all we're doing. We're just testing intervals. Now I get to pick my favorite values from those respective intervals. So something smaller than -1/2, I'm going -1. Something between -1/2 and 0, -1/4 looks dandy. Between 0 and 4, I'm going with a 1, and to the right of 4, I'm going with a 5. Okay, these are sacrificial test values. All right, now I plug them back into the full-fledged factored version, and I'm only interested in the sign. Bless you. Now, look at this right here, x squared. Do I really need to plug any of those into x squared? No, because are they going to affect the sign? What's any number squared, positive or negative? Positive. So this first factor is always going to be positive, and positive factors don't change signs, right? So I don't even have to worry about plugging into this piece. In fact, if you had any factor with an even exponent, it's not going to have a sign change there. If you look at the graph of x squared, it bounces at 0. It's positive on both sides. So I just need to plug into here. So let's see. If I plug in -1 in, I get -2 plus 1 is negative, and -1 minus 4 is negative. A negative times a negative times a positive is positive. Now, you don't have to store all that in your head. You know, if you need to, you could just say, okay, that's going to be a positive times a negative times a negative. And then you can come over here. And I put a -1 accidentally. A positive times a negative, that's a positive times a positive. That's a positive. The chart is there to help you. So, you know, whatever you need to do. Okay. -1/4. Let's go. We'll plug it back into. This is always positive. -1/4 times 2. That's -2/4, also known as -1/2. -1/2 plus 1, positive. That's positive. And then -4 minus 4 is negative. So a positive times a negative is negative. All right, negative. Now I plug in a 1 and I get positive times negative, which is also negative. No sign change there. And then on 5, I plug in a 5 and I get positive, which is positive. All right. So now if we're going to ask where f is increasing and decreasing, we have the intervals here. We'll say f is increasing on the interval from -∞ up to where? -1/2. See where you can look back and see the -1 there, and it's tempting to use the -1. Again, after you use those values, if you want to like cancel them out or circle these guys up here, -1/2. Union 4 to infinity. And if we had to write the reason, let's go ahead and write it. Because f prime is greater than 0 on these intervals. They used to give you credit for the number line chart, but like starting like 2008, they're like, no, we're going to make them interpret it for us, which I like it. Okay, so there's that. And again, another judicious use of a pronoun. What's the antecedent to these? These guys right here. I clearly see them. Okay, and then in a separate sentence, I'm going to come up here because I'm running out of room up there. F is decreasing on. Now this is interesting. Do I have to step over 0? Can I go from -1/2 all the way to 4, or do I have to split it up in 2 intervals?
You got to split it up.
You can. Yes. but you don't have to. It all depends on how you write it up. When we call these singularities like x cubed, okay, what this graph looks like is this. If you want to draw it, it goes from increasing to decreasing, and then it's decreasing on this side and decreasing on that side. So it's kind of like a negative x cubed. And then it goes from decreasing to increasing. You can say that something is decreasing through a singularity. It's okay to do that, but your justification is slightly different. Watch. If you want to say f is decreasing on, bless you, -1/2 to 0, union 0 to 4, that would be fine, right? But your reason would be because f prime is greater than 0 on these intervals. And there's nothing wrong with that. You can certainly do that. Did I say greater than? Yeah. Okay, my bad. See, I would lose a point right there. I know what I'm doing, but I'm not doing it. Stick it to the man. Who's the man? I'm the man. I'm sticking it to myself. Or do this. Or you could say from -1/2 to 4. But now you would say because f prime is what on these intervals?
Less than or equal to.
Excellent.
Good job, Bo.
Less than or equal to. Yeah. And so that's one of those, if you don't want to even tangle with that, you don't have to even mess with that. It comes down to like the definition of increasing and decreasing, whether we can choose endpoints. If you have a horizontal tangent, but it's increasing on both sides, we can say that it's monotonic increasing because it's a singularity. Now, if it happened on any kind of interval and not just at a point, well, then we have a problem. Okay, so we call those singularities. So either one is correct, but notice the justification is slightly different. All right. Okay, now to the local extrema. The question may ask you to find the x value of the local max and the local min, and that's it. If that happens, all you got to do is justify the first one and the last one. You wouldn't even have to mention the one that didn't work. Okay, so you got to read carefully. That's what happened up here on example 2. Right, example 2 said I added find the x values of any local extrema. That's all I said. But down here, this is why I changed the wording. Sometimes it says this: at each critical value, CV, determine if f has a local max, a local min, or neither. So if it says it that way, now you need to address every single critical value, including the ones that don't pass muster for local extrema. Okay, so let me show you what the wording is for that. We have the results right in front of us, yes? That number line chart gives us so much information. It's just a matter of, can we get full credit? Don't say it has a local max, because what is it? What's the antecedent to it? What? It could be what? What did you say? That could be f prime, but what else could it be? It could be Jackson. Yeah, we haven't defined what it is. Jackson, are you it?
Are you an it?
It could be. So if we say f, now there's no ambiguity. F has a, let's go from left to right, a local max at x equals -1/2 because, okay, now here it is. You're going to get a point for the correct answer, but the because part is the justification. And again, it's because f prime changes from positive to negative, not in France, but at x equals what, Ethan? Where does it happen? At the ROTC building or where? Correct, at -1/2. Pay attention. Come on. You won't fall asleep if you're engaged. Right? You ever fall asleep on the wrestling mat right in the middle of a match? Nope. You know why? Because you're engaged. There you go. Student of the month. Okay. Let's go. Let's go. Let's go. At x equals -1/2. Okay, so that takes care of that one. Let's do the local min next. Okay. F as a local min or a relative min. That's more letters, but it'll work. And it's okay to abbreviate max and min at x equals 4. Okay, comma. And once you have this style down, it'll translate to everything else we do the rest of the year, because we're going to be doing this with the second derivative as well for concavity. And the phrasing is exactly the same, because f prime changes from negative to positive. And where does this happen? Not in France, but at x equals 4. Or you can say at this point. But if you write out the words this point, then compare it to x equals 4, it's more strokes. So, right, you just got to refer back to it. Now, if it only asks you to find the x location of the local max and mins, we're done. But if it says at each critical value, max, min, or neither, now we got to address the other one. So how do we turn that one into a local argument? This is the local argument because we're talking about a sign change at a point, and that implies locality, relatively small interval, immediately to the left, immediately to the right. How do we do it with it when it's not? Well, let's try it. F has, and this is going to be a lot of writing. F has neither, whatever you say, a local max. Is it or nor? Nor, right? Oh, I was just reading that same magazine that, the text messaging over the years has kind of eroded the human language, but now it's gotten even worse, and they're blaming it on the pandemic with all the Zoom calls. The Zoom calls have always been a lot more informal, where people are on mute and they're not have to communicate, in a business setting. So people are starting to curse a lot more curse words, and the communication. Yeah, they don't know rules of grammar and stuff. Anyway, we got to fight, right? We got to preserve, right? Not all change is progress, right? Not all change is progress. F has neither a local max nor a local min at x equals 0, right? I'll look back up here to make sure. Yeah, at 0. And now how do we write it? What would you suggest? Go ahead. Since the signs of what? The signs of F prime stay the same. Stay the same. Not quite, but that's a good start. Let's go ahead and write down the first part of what you said. Because or since, you could actually use since, because the signs of F prime are, you said the same. We need to be a little bit more specific than that. No.
Equal to 0?
No. Don't change because they're what? They're both what? They're both negative. You have to talk about not what the sign is. The signs of F prime are negative. You can't just say the same. They are negative on, and then here's the magic word that implies locality. Either side of x equals 0. That is the magical word that implies locality. You can't just say that F prime is less than 0 to the left and right of x equals 0, because that implies everywhere to the left and everywhere to the right. But when you say on either side, that implies immediately to the left and immediately to the right. So you had it there, Mason. That was a good start. Now, is there a faster way to write the signs of F prime are negative? Yeah, because F prime is less than 0. So yeah, this whole thing can be replaced with this. Are they both okay? Absolutely. Absolutely. When in doubt, write it out with words, right? But if you can, when you can, use the language of math, because it is a legitimate language, right? Let me not highlight either in orange. Let's highlight these. These are interchangeable. These are the same. But either side, we'll do green. That's the magic word. Okay. Now, if you happen to eventually see some scoring guidelines that College Board has put out, they do it a little bit differently. They do, and it's a lot more writing. Okay, but this way is golden. It works. Okay. All right. So you can kind of see the kind of the template for all these sentences. They're really the same. We start with the name of the function, f or f prime. We say at this point x equals, and then because, and then we always talk about a specific function, f prime or later f double prime, change signs in the following manner, from positive to negative, and where? Not in France, but also at that same x value to which you have already referred. Okay. Super important. Very important. How we doing? How we doing on time? That's a great place to stop.
3 minutes.
That's a good place to stop. Anyone know any good, let's see, it's National Bird Day jokes. Anyone know any good bird jokes? I tried to make one up last period, but it didn't fly. Penguins. Oh, you had one. I didn't even hear you because Mason's just so loud with his brilliance. Because yeah, Mason for student of the month next month, February. Go ahead. What's your bird joke? We're recording bird joke. What is it? They all flew out of your head. I get that. Anyone know another bird joke? Let's think of one together. Someone come up with a bird species. We're gonna write a bird joke here in the last 3 minutes. A swallow. Let's choose a different bird.
Let's not use swallow.
The titmouse.
Yes. The blue-footed. That's not much better.
Yeah. The blue-footed booby.
Yes. They have one.
I'm the blue-footed booby, and I love to do my dance. I'm a blue-footed booby, and I'll put you in a trance. I'm a blue-footed booby, and I love to do my dance. Because I'm the blue-footed booby. Someone help me find my pants.
Yeah. They're in France. Is that a real song or is that a
I just made that up. That's good. How'd that work?
There's a brown booby at Canyon Lake.
Okay, now I'm interested. There was a booby at Canyon Lake?
There was.
Like somebody like brought it from like the Galapagos?
No, it came. It flew all the way here, and it was at Canyon Lake on the dam, and it was there for about 2 months.
Damn.
Mhm. Me and my grandmother, my nana and I went to go see it.
A booby on the dam?
Brown booby on the dam.
A damn booby.
It was a damn booby.
That was a damn booby at Canyon Lake.
It was huge.
Did you cover your grandmother's eyes?
I did it. We got so many pictures of that booby.
Can I see a picture of that booby?
I'll bring in some. She's got so many.
Don't text it to me because I don't want to be caught with a damn booby on my phone.
I'll have my nana send it to me.
Okay, if you just show me on your phone.
Whoa!
All right. Y'all have a great day.
Hey.
Bye-bye. See you, Ethan. Congratulations. You're welcome. You have to be awake to hear it.